Leave a hot cup of coffee on the counter, and it always cools down to room temperature. It never spontaneously heats itself back up. Drop a glass on the floor, and it shatters into pieces. You will never, in the history of the universe, see shattered glass spontaneously reassemble itself and jump back onto the counter. That one-way street, order breaking down into disorder, energy spreading out and never spontaneously reconcentrating on its own, is one of the most airtight, universally confirmed laws in all of physics. It's called the Second Law of Thermodynamics, and physicist Arthur Eddington once said that if a theory disagrees with it, that theory has no hope but to collapse in deepest humiliation. Today we're going to look at why this quiet, unglamorous law of physics, one you've experienced 1,000 times without ever thinking about it philosophically, has some surprisingly large implications for whether the universe had a beginning, where it's headed, and why both of those facts sit far more comfortably inside a Christian view of the world than a purely naturalistic one. Let's get the physics straight first, because this law gets casually misquoted a lot. The second law of thermodynamics says that in any closed, isolated system, the total amount of entropy, a measure of disorder, or more precisely, the number of ways a system's energy can be arranged, will either stay the same or increase over time. It never spontaneously decreases. Usable, concentrated energy naturally tends to spread out and become less usable, less concentrated, less organized. A hot object cools down, and that heat disperses into its cooler surroundings, rather than the reverse. Energy isn't destroyed. That's a different law. The first law, about conservation. But its usefulness, its ability to do organized work, steadily runs down. This applies to the entire physical universe, considered as a whole. Stars burn through their nuclear fuel and eventually die out. Usable energy in the cosmos is gradually converting into less usable, more evenly spread out forms. This isn't a fringe or contested claim in physics. It's one of the most thoroughly tested, most confidently held laws in the entire discipline, verified in millions of experiments across more than a century, without a single confirmed exception. Here's where the second law starts doing serious philosophical work, and it connects directly to the column argument and Big Bang cosmology we covered in an earlier episode. If the total usable energy in the universe is constantly running down and it never spontaneously runs back up, then think about what that implies if you run the clock backward instead of forward. If the universe had existed forever, an infinite past with no beginning at all, then it would have had an infinite amount of time already available to run down completely. Entropy would already be maxed out. Every star would have already burned out. Every temperature difference would have already evened out into a uniform, lifeless, motionless equilibrium. Physicists sometimes call this hypothetical end state heat death. But that's not what we observe. We observe a universe still full of burning stars, active galaxies, and usable energy differences everywhere we look. A universe that clearly has not yet run down to that final maximum entropy state. And if a process that constantly runs down, never resets, and never runs backward, hasn't yet finished running down after supposedly infinite time, something doesn't add up. The far more natural conclusion is that the universe hasn't had infinite time to run down at all, because it hasn't existed forever. It started at some finite point in the past, with a highly ordered low entropy beginning, and has been running down in one consistent direction ever since. This gives us a second independent line of physical evidence, separate from the Big Bang expansion evidence we covered before, pointing toward the same conclusion. The universe had an actual beginning, a specific starting point, rather than existing as an eternal, past infinite process. There's something even stranger buried in this law that's worth pulling out, because it touches on something physics still hasn't fully explained. Most of the fundamental equations of physics, Newton's laws of motion, Einstein's equations, the basic equations of electromagnetism, work exactly the same whether you run time forward or backward. Mathematically, most of physics doesn't actually require time to have a preferred direction at all. And yet, in our actual lived experience, time clearly does have a direction. We remember the past, not the future. Causes precede effects, never the reverse. And entropy only ever increases, never decreases. Physicists refer to this observed one-way flow as the arrow of time. And one of the deepest open questions in cosmology is explaining where that arrow actually comes from, if the underlying equations themselves don't seem to require one. The leading explanation ties directly back to what we just discussed. The universe appears to have started in an extraordinarily special, highly ordered, low entropy initial state, a state so improbable, so exquisitely unlikely to have occurred purely by chance, that physicists like Roger Penrose have calculated its improbability using numbers so large they're almost impossible to write out in ordinary notation. The arrow of time on this view is really just entropy's arrow, the universe consistently moving away from that remarkably special starting condition in one direction ever since. So we're left with two connected mysteries stacked on top of each other. Why does time have a direction at all, when most of physics doesn't obviously require one? And why did the universe begin in such an extraordinarily improbable, highly ordered state in the first place, rather than starting in a much more probable, disordered one? Both point toward the same underlying fact, a very particular, very deliberate-looking starting condition, not a random or inevitable one. Here's where this connects to the larger theme running through this whole series. A universe with a definite beginning, an extraordinarily ordered starting condition, and a consistent, one-directional history moving toward an eventual end. That's exactly the kind of universe Christian theology has always described, long before modern thermodynamics existed to confirm any of it. Scripture doesn't describe a cyclical, eternally repeating cosmos the way some other ancient and modern worldviews do. It describes a linear story, a definite beginning. In the beginning, God created, a history unfolding with real purpose and direction, and a definite culmination still to come, described in passages like Romans chapter 8, where creation itself is described as groaning, subjected to decay, waiting for eventual renewal and restoration. That's a strikingly good match for what thermodynamics actually describes. A universe that started in a special, ordered state that has been running down in one consistent direction ever since, and that is physically headed toward some kind of definite endpoint, rather than persisting unchanged forever. A purely cyclical or eternal universe, the kind many ancient philosophies, and even some modern physicists have proposed, doesn't sit nearly as comfortably with what the second law actually tells us. A universe with a beginning, a direction, and a destination does. So why does entropy matter for faith? Because a law of physics you've experienced every single day of your life, coffee cooling, glass shattering, ice melting, turns out to carry real weight in the biggest questions this series has been asking all along. Did the universe have a beginning? Is it moving somewhere, or just persisting forever unchanged? The second law of thermodynamics answers both questions the same way modern cosmology does. Yes, it began, and yes, it's headed somewhere. Not nowhere. Scripture described a universe with a beginning, a direction, and a coming end long before physicists could measure any of it. Maybe that's not a coincidence science stumbled into. Maybe it's a story that was true all along, waiting for our instruments to finally catch up to it. Thanks for watching. If this gave you something to think about, consider subscribing, and I'll see you in the next one.